railroad position was as trainmaster at Ashtabula Harbor, Ohio, and you'll have to be sure to ask him stories about what that job and various successive positions were like. He worked at Conrail for more than 10 years in various positions in the engineering, sales, marketing, and transportation departments. He holds a BS in metallurgical engineering from the University of Texas at El Paso, an MS in material science and engineering from Case Western Reserve, and an MBA from St. Francis University in Colorado, Pennsylvania. He's authored or co-authored more than 90 technical papers, which is a record that would be enviable to anybody in academia, and has made numerous presentations on a variety of railroad industry subjects, including wheel processing and performance, axle processing and performance, and thermite rail welding. He's also an active member of the ASME Rail Transportation Division, where he served as their chairman from 2008 to 2009. Please join me in welcoming our speaker, Mr. Cameron Lonsdale, who will present the William W. Hay Railroad Engineering Seminar today on recent research to better understand wheel rim, axial residual stress, and vertical split rim wheel failures.
Thanks, Chris. I've seen an awful lot of good research work come out of this university over the years, and I'm going to talk a little bit about the other side of the wheel-rail interface, the wheel side today. In fact, much of the wheel research was done here under Professor Wittenkamp some years ago. So this is really appropriate that we're giving a talk on wheels at Illinois. So here's the outline of our presentation. I'm going to talk a little bit about what is a vertical split rim, or VSR as we call it for short. Give you some background information. I'm going to go through what I call the VSR puzzle. There are about roughly 300 of these a year in North America, and that makes finding the smoking gun a little more difficult because there's relatively few of these failures when you consider the entire population. I'm going to talk about some work we did at a drop hammer to try to create a VSR. I'm going to look at some residual stress measurements from the tread surface of the wheel that we started with initially and found to be not completely satisfactory, so we moved on to using radial slices of the wheel to look at X-ray diffraction. I'm going to be talking today almost exclusively about axial residual stress. That's across the rim section, as if my thumb is the flange going across the rim section, as opposed to circumferential or hoop stress. We're looking almost exclusively at axial residual stress here, and that component only. I'm going to be looking at measurements we took at and away from failures, and we'll also be looking at the effects of out of round on axial residual stress and wheel truing or reprofiling the wheel tread on axial residual stress. This is what a VSR is right here. Basically, you have a piece of the front rim face of the wheel break off, and it can be a relatively short circumferential section or, in fact, a very large circumferential section breaks off. And what happens, of course, when it gets narrow, it can drop into the gauge and cause a derailment. Occasionally, they go this way, and the back rim face breaks off of the flange, but the vast majority occur in this fashion right here. And so the axial direction is this way, so we're interested in what is the axial residual stress in the wheel in this direction. Obviously, if the rail is here, we're loading and trying to bend this open, so you can see that you have a bending load here as well as whatever residual stress is in the part. This is a really, really good picture of a VSR by Matt Dick and Hans Ewan from a paper some years ago. In fact, I think it was at one of the BNSF wheel shelling meetings where this was given. And so I borrowed, quote unquote, this picture with Matt's permission. It's a really good picture. And so here you have a wheel tread. This is the flange of the wheel up here. You've got tread damage around the wheel from shelling or spalling. You get an initial burst from the shelling and spalling. Here's the blow up of that initial damage. You can see the cracked chevrons pointing back to the tread surface. And here's the divot from the tread damage. And then, as time goes on in service, the crack tends to propagate away from the initial burst. You can see the arrest marks here quite well, and eventually it hangs by a thread and breaks off. This happens relatively quickly. You can see these crack arrest marks are moving very rapidly. It's not like you have a very large area of fatigue propagation. So a very good picture nonetheless tells you what a VSR is.
Cameron, when you say quickly, do you mean over a matter of minutes, hours, days?
Well, we're really not sure, but we think it does happen in, let's say, days or less. Because you have this zone here where these cracks are moving quite rapidly. And even in this zone here, it's not a fatigue surface really. You can see the big burst, the crack chevrons pointing back. So you may have a, what we would say, very low cycle fatigue event happening here. And then once that crack starts moving, with the relatively low ductility of a Class C high carbon steel, 1070 steel, there's not a lot to stop the crack. Here's some tread damage. It can be better, it can be worse than this, but VSRs do start at tread damage. And that's one thing that we've seen almost everyone has. And in the case where there's been one or two that hasn't, we believe that what happened was it did have tread damage, was remachined, reprofiled in a wheel shop, and they didn't get all the crack damage. So this is very significant. And if you go out and look at wheels in service, you can see some that look a lot worse than this. And I've got some pictures later on too. So again, a summary from Matt Dick's paper. VSRs can be 15 centimeters to the entire circumference of the wheel on occasion. You'll have big sections of pieces of the front rim face breaking off. VSR is typically 25 to 70 millimeters in the wheel's front rim face, as I showed you in that radial section there. Heavy cars have similar numbers of them, 263,000 pound gross rail load and 286,000 pound gross rail load. We're seen to have similar numbers of VSRs. These were on 68 wheels. I believe they were all from BNSF and UP, if I'm not mistaken, but they had a sample that they looked at. Interestingly, covered hoppers had the most VSRs, with 15 of 17 of them occurring on the B end. Now this is important. We don't know if those cars were truck-mounted brakes or foundation brakes. If they were truck-mounted brakes, then that's very significant. With a truck-mounted brake, if you put the handbrake on the B end, then the wheels on the B end can be slid. Okay, with foundation brakes, you put the handbrake on and all the wheels are effective. It's an interesting finding to me that these cars, covered hoppers, which gets set in and out of industries and grain elevators and so on, they had a disproportionate number of the VSRs occurring on the B end. So were they truck-mounted brakes? I don't know, but it's interesting.
We've got a question from someone who dialed in. They want to know where the residual stresses come from.
Okay, there is a certain amount of residual stress from manufacturing, but I'll show you as we go through the slides that the axial residual stress does change significantly from when a wheel is new and it comes from rolling and pounding in service. If anybody has any questions, just go ahead and hit me as we go. That way you remember what it is and we're not going back slides later. So just ask if you got a question, please. Of these wheels that they examined, 62 of 68 were on 36 or 38-inch wheels, which are more heavily loaded wheels, 263 gross rail load or 286 gross rail load. Only 6 out of 68 were 33-inch, so more lightly loaded. Not all were thin-rimmed wheels. At first you might think, okay, well that front rim face is going to break off. It's a real skinny section. Not always the case. And most VSRs had hollow tread wear. In other words, the brake shoe and the rolling of the wheel on the rail had left a hollow area on the tread surface, which can lead to very high stresses from rolling contact fatigue due to the geometrical change right at the edge of that hollow. And with more stresses from rolling contact fatigue is more fatigue damage.
The ones that were not hollow treadwear, were they machined to exclude that?
These were as received broken wheels at the lab. And so the ones that they said didn't have hollow tread wear just had a relatively normal worn profile, as opposed to one that was really hollowed out that had not been reprofiled in some time. And we'll see later that wheel truing does have a rather important effect on axial residual stress. Most of them were common in the winter months. Not surprising, again, you have issues with brake systems in the winter. Air brake systems can freeze in the winter. You'll get more wheels sliding in the winter. And also, fracture toughness being what it is for a 1070 carbon steel, things are more likely to break in the winter. They noted that most of these vertical split rims were impacting, as noted by wayside impact detectors. The railroads have these detectors to measure wheel impact loads. And most of these VSRs were impacting, meaning their load, as noted by the detector, was above the nominal load. It could have been 40,000, 50,000. pounds instead of the normal level. And both cast and forged wheels have VSRs. One of the fortunate things in my position is I made forged wheels for 10 years, so when people say, do only cast wheels have VSRs, I say, well, no, because I had lots of them in my former life as well. So this is a problem with all wheels, not just one particular type. So the VSR puzzle is what we called it. You know, we looked at a lot of these over the years, and Griffin has a lot of smart people, and Standard Steel has smart people, and TTCI did, all the railroads do. We've been looking at this over the years, and we could not conclusively identify what is the root cause of the vertical split rim. You look at these wheels, and there was nothing abnormal about the material. The macro etch looked good, the hardness looked good, the cleanliness looked normal. There was no evidence of thermal overload. And in fact, TTCI recently looked at 30 VSRs and did microcleanliness tests under the thought that maybe it was a cleanliness issue. And 28 of the 30 VSRs passed the AAR microcleanliness test. The ones that did not were made before the test was put in. So these were all things that really caused us to question, what is causing these? We couldn't find it. We also tried to create a VSR in a lab, thinking that perhaps it was an impact. Maybe the front rim face hits a guardrail. Maybe it hits a frog extraordinarily or a crossing diamond, and that would cause that to snap off. That was our first thinking. But we hit a severely tread damaged wheel more than 30,000 times in a drop hammer with over 200,000 pounds per load, and we couldn't break it. So at that point, that kind of discounted that. We also went through and said, all right, maybe there's something different about the ultrasonic data for VSR wheels. So we went back and we collect the maximum ultrasonic signal during manufacturing. We wanted to see, is there anything different with the population of wheels that have been manufactured in general versus the VSRs, and the UT max signal data was the same for 26 VSRs versus 24,000 normal production wheels. So again, no ultrasonic anomaly that jumped out and said, oh, these are clearly different, that's why they broke. Also, along the cleanliness line, we were thinking, all right, maybe the sulfur and phosphorus levels for VSRs were higher. With higher sulfur, you would have more manganese sulfide inclusions naturally. So we thought, well, maybe the VSRs had higher sulfur. And in fact, the sulfur level was less than the sulfur and phosphorus level for normal production wheels. So that put that out of our mind. So, again, trying to create the VSR in the lab setting. We selected some tread damage wheel sets that could be susceptible, we thought, to impact damage. We collected these at a railroad up in Canada, brought them down to our drop hammer, which is in Camp Hill, Pennsylvania, near Harrisburg. And this system is designed to test end-of-car cushioning units. You want to make sure that the coupler and the end-of-car cushioning system is such that it has sufficient cushioning ability that the car structure isn't damaged. And that's what this drop hammer is used for, to test these end-of-car units. And we were wanting to know what impact load and location on the wheel rim specifically would lead to a fracture that resembled a VSR. Now, Griffin had done this with shattered rims some years ago on a dynamometer that they have in Bensonville near Chicago. And they actually created a shattered rim defect by doubling the wheel load and testing periodically with ultrasonics to see if you created a crack and then reloading it. They actually did this successfully with shattered rims, so that was our natural thought, was to do what we'd done before. So we hit it more than 31,000 times in a drop hammer with somewhere between 250,000 and 300,000 pounds. Drop hammer is good for 1 million pounds, by the way. These would be above even the worst in-track loads. I think some of the worst in-track loads might be 200,000 pounds, so we were well above that. And as the test got to a close, the guys got more and more aggressive because they wanted to break this wheel, and I wanted to break it too. So they were mostly up around the 300,000 pound level. But what happened was the guys would work their shift in the plant and then come for the last hour of the day and try to break the wheel. So it was a big event, you know. So, well, then we didn't break it, and eventually they had to go back to testing draft gears, and we had to remove our equipment. But we did severely damage the rim. And here's this this thing here. What you do is you raise it up and then drop it, and that gives you the loading. They had to remove some of this equipment in here. This thing could go possibly up to 2 million pounds if we needed to. And here's where the wheel set installed. Some of the issues that we had was making sure this thing was strapped down properly. We actually strain gauged this wheel to try to get real good stress levels from that impact, but there was so much motion, you can imagine hitting it with 300,000 pounds. The thing jumps, the floor even moved. There's a dance studio next door. It was quite funny. They wondered what we were doing over there. It's true. Yeah, you can't make some of this stuff up. But the impacts were extremely severe, and I'll show you the damage that we ended up creating. This is what we did to the front rim face of the wheel here. You see this mushrooming, and you can see it really deformed. This was the tread damage, and I had just picked this wheel randomly and said, oh, that has a lot of tread damage. That might be a good candidate. Because we didn't know at this time. And as we go through this presentation, keep in context that we didn't know at the time. We just kind of kept stepping forward, saying we learned a little more, learned a little more. But in any case, we did severely deform this area of the wheel, and so we at least achieved that much. And I'll show you some stress results from this later. So if you look at 9.4 feet circumference, we basically achieved 54 miles of service to that wheel by hitting it 30,000 plus times, which isn't a lot. Some wheels go a lot more than that. And I suspect that if we had kept hitting it for another, I don't know, pick a number, 30,000, 50,000, 60,000 times, we probably would have broke off the front rim face. It eventually would have given up. But the point here is that many cars go in service for hundreds of miles at levels lower than that, let's say 60,000, 70,000 pounds. So you have to ask yourself the question, what's worse, 200,000 pounds for 50 miles or just below condemnable at 80,000 for 6 months? These are the kind of fatigue questions that you start to ask yourself. We then did some very simple FEA work, and we looked at a thin rim wheel, a 7/8 inch thickness rim, and we put a 100 kip point load 1 inch in the front rim face. And what we were trying to do there is say, all right, what stresses are generated when I point a load right here to try to bend that crack open? And what was really interesting is that we showed at the tape line of the wheel, which is the center of the tread, we showed with a 100 kip load 28.5 KSI. At 200 kips, since it's linear, you would be almost 60,000 pounds, or 60,000 PSI, not a trivial stress level at all. And what really helped solidify in my mind how these cracks propagate was that we looked at the hoop stress generated at the front rim face. From that point load, it creates a hoop stress in this direction that in fact is almost 29 KSI for a 100 kip point load, and you could double that for a 200 kip point load. So that explains why this crack not only bends open, but then starts to move circumferentially away. So if you have tread damage and it's pounding on that point, that's what's happening. Yeah, I'm a visual, I have to see it. Yep.
What was the load rate of the drop hammer, like in between drops?
Very slow. What happens is it's manual, and a guy in a control booth pushes a button, it raises it so many inches, and then there's a relay, he pushes a button, and it drops. So we probably got 3 a minute, pretty slow, really slow in fact. Obviously you'd want something that would be more reciprocating if you're going to do this the right way. So. Yep.
This stress that you're quoting, rolling contact fatigue, you get primarily compressive stresses, as you know. So this is some sort of a bending stress? Or?
Yes, this was a simple point load in finite element where we just looked at, what is the stress distribution on a plot, and it showed us that at the tape line, you had essentially a bending moment, okay, that would cause that to open up at the tape line. Therefore, if you had tread damage and a crack there, and that load was applied, it would want to bend that open. And of course, the axial stress would then be additive to that. So we were convinced at this point, all right, we've hit this thing 30-some thousand times with 250,000 pounds. We can't break it. We've done finite element work of various types. We can't see stresses that are really clear to us why this should break. So we contacted Lambda Research in Cincinnati. We've used them before. And we said, we need to start looking at residual stresses in these wheels, in used wheels, broken wheels, new wheels, and so on. These people are very good down there. And if you ever have any residual stress work, I'd recommend Lambda. We started with X-ray diffraction and core drilling from the tread surface because we didn't know any better. As a first cut, let's just start taking some measurements from the tread surface. Again, looking at the axial stress, not hoop. People have looked a lot at hoop over the years, but we're not doing that here. And we just did some initial testing to see, is there any difference between a new wheel and a broken wheel?
Question from
Yep.
how a hoop stress resulted from point load.
Yeah, basically it's it created a bending, and then when you look at the finite element plot going away from that on the front rim face, there was a hoop stress in this direction, circumferentially around the wheel from that bending load. We looked at the tape line and out at the edge of the front rim face. So core drilling was our next step. And what you do is you put a strain gauge in, and then you have essentially a core drill, a trepan that goes down around that, and you look at how the stress is relieved. This was the X-ray diffraction from the tread surface, and very close proximity to each other. So here's the results for a new wheel, and here's the results for a broken wheel. And this got our attention. We said, well, isn't that interesting? This is the tread surface here. This is depth below the tread here. So what you have is right at the tread surface, it's slightly more in compression, and then it levels out. This is 1/3 of an inch deep, not very deep, and I'll get back to that.
Cameron, I'm sorry. Can you utilize the mouse on
Oh.
the computer, the trackpad?
Okay.
When you're doing that, so that the people
Sure.
who are signed in remotely can see it also?
Okay, this is the, whoop, I jumps, how do I do this now? This is the tread surface here, and this is depth below the tread surface.
It's still not working.
Okay.
What? Oh, see, all right. Okay. Okay, so this is the tread surface here, and this is depth below the tread surface here along this axis. And so you have a new wheel that is relatively close to neutral in the axial direction. Whereas for the VSR wheel, you've got a completely different profile, a completely different stress profile. And this got our attention, and we said, all right, maybe there's something here. So we talked to Lambda, and again, the other problem with core drill and X-ray for the tread surface is you can only get 1/3 of an inch deep. You don't know what's going on within the wheel rim itself. You can't tell stresses at an XY coordinate within the steel piece. So we needed to know the stresses at locations below the tread surface, and we asked Lambda about how to do this. Again, focusing on axial residual stress. One big question was, do we need to strain gauge a wheel every time to get the correction effect when we cut out pieces? This was really important because if you're shipping an entire wheel, it's a pain in the neck. If you're cutting out radial slices at a machine shop, you can just send them by US mail, little pieces. So this was very important, and Lambda did this on a wheel. They strain gauged the wheel, we cut a piece out, a section out, and they said, hey, it didn't make any difference in the axial direction. It certainly would in the hoop direction, in the circumferential direction, because when you cut that, you're relieving the compressive hoop stress that's in the wheel. But in the axial direction, it had no effect. We also use American Stress Technologies in Pittsburgh, and they confirmed that yes, if you're cutting slices out, it has no effect on the axial stresses. Here's the first wheel that we did. The slice that we cut out was a big slice. We've subsequently gotten much thinner on the slices instead of this big pie shape.
Sorry, but
Yep.
the stress profile was quite interesting. Can you go back to it?
Sure.
We kind of went too fast for those.
Yep.
So, if you look at your stresses on a new wheel, first of all, they're not self-equilibrating, right?
Correct.
What is Lambda's response to that when you got this result from them?
Well, first of all, we're only looking at one component. So if you've got axial,
You've got the three components there. Hoop, axial.
yeah, right. But
And you don't have the
radial,
radial one.
we don't have radial, so we don't know what that
Which
is.
very small.
Right, you would think that it is. And we're only going 1/3 of an inch deep. As I'll show later in some of the work we did on the slices, you do have the equilibrium, you have tension deeper. So I suspect that if we were able to shoot from the tread surface much deeper, we would see the balancing portion of the tension. And we do see that in some later work.
This is a rim quenched wheel,
That's correct, yep.
cast.
This one was cast, yes. I've got data for forged and cast later.
Thank you.
But this one, let me use this, let me get back over here again. There we go. This does have some tension balancing, as you suggest, yep. And that's very important because you can't just have just compression. So here's the slice. We're now looking at the radial slice that says tread surface and rim face. And it shows axial direction again. And this is really what we did. We cut out slices and started taking measurements along the black line, the black vertical line. This area was electropolished first so that you could take X-ray diffraction measurements out. They have to get below a depth where surface effects don't matter anymore. And they do that on every slice to make sure they're not looking at cutting or sawing effects. And then we took a series of shots going down below the tread surface. This particular group of measurements was at 1.5 inches from the front rim face. We also took some at 3 inches from the front rim face, just to see if there was any difference there. Okay, a very busy graph. I think I'm going to have to use the mouse thing for this one. I can find where it went. Maybe I won't use it. I won't use it. Again, the tread surface is the vertical axis. The horizontal axis is the depth below the surface. You see that you have, at the time we did this, these were the number of wheels that we had tested. 5 VSRs, 4 new, 5 used Class C wheels. They're used but not broken. We also tested some untreated wheels that were not rim quenched. And we looked at the time, 2 forged wheels. And what we have here is we have a deep area of compression below the surface. And then you have the balancing tension, as you suggested earlier. And the VSR wheel, the average for the VSR wheels, is seen to be the highest. Of interest also is that you have the new wheels are relatively near zero. There is some measurement error with this, and there has to be balancing tension in there at some point. But again, we don't show the hoop or the radial in this. But you can see that the new wheel, the red dotted line, is significantly different than the blue vertical split rims. And this really got us interested here, because now what we have is a situation where you've got compression on the surface from rolling and pounding, and if cracks can extend down into that tensile zone, then you can have problems. The 3 inch from the front rim face work looked almost the same, very similar. Yep.
But this, I was wondering about this when we looked at your earlier chart, and this, I think what's interesting also are the used Cs have a pattern that's very similar.
Exactly. Exactly.
So I was wondering if maybe the ones that suffered VSRs were different, to suggest they weren't different.
Well, as we go along with this, what we've proposed is that a VSR is kind of an A plus B plus C situation. You have to have tread damage. You have to have tread damage with cracking that gets deep enough, and you have to have that tensile zone that those cracks reach into. And if you don't have those things, then you won't have a VSR. What's very interesting also is this, the used U wheels. You'll note that the tension is much deeper. Now, this is only a 3-wheel average. We tested one to start, and we found the same result. We said, this is interesting. Why is this? Because we never saw VSRs to any great number with untreated wheels, which were not rim quenched. It's a softer material.
Did you look at the hollow worn parameter in relation to the stress profile?
No, we did not. We were doing this completely independent of anything other than just stress levels and whether it was used, broken, or new.
What is the resolution, spatial resolution in this case, I assume this is in the axial direction, right? This is depth from the surface. Okay.
Yes, correct.
So what is this lambda when they give you these residual stresses? How much resolution in the distance can they resolve these stresses?
In other words, what's the plus minus on the value that they give you?
Yeah, I mean they have some
Yes.
sort of an X-ray beam, right? Or
Yep.
some
Yep.
refractive beam. So that beam is of the order of millimeters, or I don't know what it is exactly.
I don't know. I can look that up. We discounted. They would give you the nominal and then the error of the measurement. We just threw away the error and said we're just going to go with that number.
So you have a very fine, relatively fine-grained structure, like you said, because it's a ring-quenched wheel. Maybe, I don't know what it is, about 50 microns or something like that.
Okay.
Let's say that's the pearlite column size, right? But these stresses are many, many, many grains, right?
That's correct.
The measurement
That's
is
correct.
many.
Yep.
So locally, totally different story,
Yep.
right?
Absolutely.
So my feeling is this technique, you know, okay, it's an industry gold standard and all that, was 25 years ago, cannot sometimes answer the kind of questions maybe you're looking at.
I don't disagree with you. I mean, if we took it to Oak Ridge and did some work there, you'd get much more accurate results. You know, really. I certainly don't disagree with you. The U wheels, again, this tension was pushed much deeper here for the average. And what we think was going on there, because U steel is significantly softer, it's like 280 Burnell versus Class C, which is 321 to 363 Burnell. We think what was happening is it was so soft it was deforming differently. We're certainly not suggesting that we go back to untreated wheels, because they wear much faster and because they don't come manufactured with the beneficial compressive hoop stress. But we thought this was interesting. We stumbled across a U wheel, tested it, and tested two more because, wow, that's an interesting data point. Again, the results on the line of shots, 3 inches from the front rim face, were very much similar. Yep.
How do you make sure the stress performance doesn't change as you use the wheel spot to do a test in lieu of using the whole wheel?
Okay, what we're doing with cutting a slice and taking those measurements is getting a snapshot. As I'll show you later, the stresses can and do vary circumferentially around that wheel. And that's one of the confounding things that we've gone through with this. Again, at this time we were like, is it different? What is broken? What is used? What is new? And so we were taking a snapshot at that point. If you went 10 degrees this way or 50 degrees that way around the circumference of the wheel, certainly you could have different numbers. Also across the tread surface. I'm not finding where this mouse is here. I think it's more trouble than it's worth, actually.
It's there.
Oh, there it is. Okay. There we go. Where did it go? It's gone. Okay. We'll go without it again. John Oliver suggested doing this. He is a colleague that I work with. And this superimposes the stress profiles for VSRs over top of the VSR profile. And again, I'm a visual, so this was really interesting for me to see, is that, wow, that crack starts to go towards the front rim fillet right about where it gets tensile. That's a really interesting thing to see. Is you've got the heavy compression here at the surface from rolling and pounding, and then you have this balancing tension. And that balancing tension, we think, is one of the issues that can lead to VSR formation. As we went through this, we kept taking data. We started looking at away from the failure, near the failure. I've got some additional information on this. We also tested the drop hammer wheel, which happens to be the one with the triangles pointing to the left. And we see that in that particular wheel, at a random slice location, we had a similar stress profile. We also, in the next slide, you'll see we tested the drop hammer wheel in more detail. And we looked at a series of shots, 1/2 inch from the front rim face and then 1.5 inches from the front rim face. And what's interesting about this is the 1.5 inch, or rather the 1/2 inch line of shots are the squares, and you see the compression is much, much deeper, down to negative 90 KSI, and the balancing tension is much higher, up over 40 KSI. Again, not trivial numbers when it comes to tensile stresses. So right at the lip that you saw in that picture where it was being deformed and rolled over, 1/2 inch from that front rim face, the stresses were getting very, very high. The slice that we took for this was not dead center in that impact zone. It was slightly to one side. So I suspect that right in the center of that impact zone, the stresses would be even higher. We had used that for metallography to see if we were actually creating a crack. And like I said, we had not created a crack and did not succeed in breaking the wheel. What we did succeed in doing, there's always some good that comes out of a test. We did see that right at the zone where the impact hammer was hitting the hardest, we were getting some very high tensile stresses, which tells us that wheel impacts can generate high compression at the tread surface and high tension below it, which is the problem. We kept testing slices. We have a large number of wheels we've tested. Here's some used wheels with the colored plots here. You'll see that the numbers and values are all over the place. And what we're partly confounded by is we don't know the service history of these wheels. We find them in a wheel shop. We don't know what car they were under. We don't know what happened to them. We don't know their thermal history. That's another big thing. So we collected all this data, and unfortunately, we can't tie it back just to a service cause in many cases. This is a rather esoteric point for testing, but I think it's important, particularly for a group like this. What we did is you have the fracture surface for testing at and away from the VSR. You have the fracture surface on the right side, and we took a line of shots right up next to it. And then we backed away, I think an inch or an inch and a half, and we took the blue line of shots. And I wanted to see if there was any difference there, suspecting that relaxation would be in play here. This green circle over here is where they do the test to make sure that they're below the sawing and surface effects. They take X-ray measurements until they approach consistency. And here's the results that the axial residual stress at and away from the failure edge. You see the blue line is adjacent to the crack face, and the numbers are much lower than if you back away from the crack face an inch and a half. So indeed, relaxation is important. If you're right up against that crack and you try to take X-ray measurements, your numbers are going to be a lot different than if you back away from it back into the part itself. The question here was, where do we test? How do we test? Do we test in the failure zone? Do we test out of the failure zone? Do we go around the other side of the wheel and test? All good questions, and we didn't know at first. This deals with the variation in circumferential stresses going around the wheel. What I'm showing here is the maximum axial tensile stress. So we take a line of shots and pick out the maximum axial tensile stress below the surface. So I've got the maximum axial stress here for slices tested at and away at the 1.5 inch from the front rim face level. In particular, I'll point out this wheel, the 6588166 with the 3 values. I've got 3 values, 2 of which are close and 1 is not at all close. So if I test at one location, right at the failure, and if I test away from the failure, outside the failure zone, I get 2 results that are pretty close, the 82911 and the 6811. But an earlier version tested near the failure was much higher. So this tells us we can have a lot of variation in stresses depending on what was the tread condition, how was the wheel impacting, and so on. This other wheel, the 12.53938, is the same way. I've got a relatively low tensile stress of 50 megapascals right in the failure zone, but if I go away from it, I have much higher. Part of that's probably relaxation, but part of it is variation around the wheel. And this is the problem when you're doing something that hasn't been done before. You really don't know where you should start looking. These are the compression values. And again, this one particular wheel, the maximum axial compression stress for slices tested at and away for the 6588166, we see 2 of the values tested away very significantly, and then we have the one in the failure zone that's in between. But for the other 3 wheels, the 12.53938, 796, 70824, and the 3 of 98 wheel, the results do seem to be closer together. We then wanted to get a firm correlation between total indicated runout, out of round, and residual stress. So we took a number of wheels, we put them on machining centers, and measured the out of roundness. We took the high point and the low point and took a slice from each of those wheels. Here's the raw data here. I've got some conclusions from that. For TIR and axial residual stress, the higher out of round wheels exhibit a greater maximum compression value and greater average tension value than low out of round wheels. However, the separation is not that great. If you look at the maximum axial compression and tension for the high out of round, negative 298 megapascals and plus 159 megapascals for the tension. For the low out of round slices, again, same wheel, just the lowest out of round point, the compression did show an appropriate reduction, negative 202, but the tension did not track so well. We're still confounded by this, and we're doing some more testing to try to build this correlation better. One of the things is sampling. If you've got an area of tread damage, do you take the slice at the center of the tread damage and test at the bottom of it, or do you test to the edge, where the wheel may have been impacting more? And thus far, we've gone all to the center, which may not have been right. So we looked at a B38 wheel, CB38, which was actually a D steel wheel, which is slightly alloyed. We don't expect a lot of difference in residual stress because the alloying is very slight. And we did see a better correlation here. We looked at maximum compression and maximum tension at 90 millimeters from the back rim face and 70 millimeters from the back rim face. At the high out around point, let me go back. At the high out around point, we had plus 199 megapascals, and the low out around point, plus 154. This is intuitive. It's what should be happening if you have a highly out around wheel that's pounding as it rolls down the track. Because of an out around situation, you should logically have more compression and tension. For the 70 millimeters from the back rim face, we had plus 180 for the tension at the high out around point, and for the low out around point, plus 142. So this particular wheel did behave more like we expected it should. We've got some additional work, in fact, with Dennis's folks coming up that we're going to try to tighten up this correlation. This was the first time we'd ever seen this. We found a VSR within a VSR. Here's the broken section, two adjacent VSRs, and this piece had broken off. We found another one inside it. That was very interesting. And then along measurement line B, what we did is we took a line of shots down, X-ray shots down, until we reached the maximum tension point. And then we started going toward the flange. And every one of the results along this line were tension. So we see that there's a zone of tension below the surface. So if the cracks can come down in there, and if they reach this tensile zone, that's where trouble can occur. The results on this line were all out of whack, as you'd expect, because you have a surface that's been broken and a surface here that's broken, so we didn't learn much from that.
Can I ask you a question?
Sure.
Let's say you took a Class C wheel, you did not put it in service, and you did X-ray measurements, right?
Mm-hmm.
What are the magnitude of stresses you get?
Okay, so a new wheel.
New wheel.
Let me go back and find that. Yep. That was on the one graph that showed the new wheels. So here we go. It's the red line. This is an average of 4 at the time. I mean,
Measurement by lambda, right?
that's correct. Yep. And again, the axial direction. The idea with rim quenching is to put in the hoop compressive stress. And nobody's ever thought about the axials. Axials were always thought to be this magnitude, and who cares? That was always the thought. But in order for something to break open like that, you have to have axials that are more than just these numbers.
But I think these numbers are not right, honestly. I mean, it looks too low. Even if you had a rim quenched wheel, you should get some sort of a tensile stress.
Okay, I can show you the source data that we have, and
I mean, based on finite element calculations we did 25 years ago, we were looking at about between 18 and 21 KSI.
I did have the FEA here, by the way, put on it.
Is that
Yeah.
over there?
That was it right there, and that uses the model from the U of I. There's been a great deal of discussion about what creep model is correct. So
you did use that data?
Yeah, this is from U of I right here. This is, I think, from the paper that was done here.
Well, I mean, that must have been one of my students.
Yeah, yeah.
Yeah, I mean, that's about right. It's about 20 KSI. So that's why the dashed line, your measurement surprised me a lot.
Yeah, and it surprised us too, because we thought we were going to more closely match this one.
And you should, really.
Well, some subsequent creep testing we did at Westmoreland when I was at Standard about 7 years ago, we found a lot different creep than this. So the question of what creep model is correct is important for FEA.
I would say the U of I one would be.
Oh, of course, of course, of course. But I think a lot more work needs to be done in that, particularly over temperature ranges, particularly to see what happens with creep model. So.
Good. Thank you.
I'm going to catch back up. Okay, we're going to which slide? Okay, so variation on around. Okay, we did the same thing again. This is the one that says radial slice cut at VSR origin. And did the same thing here, took a line of shots down, found the maximum tension point, and started going toward the flange horizontally. And again, this whole zone in here is tension. This is for the wheel 6588166. And again, that whole zone being tension, if a crack comes down, that could be trouble. So the failure mechanism that what we proposed up at ASME in Minneapolis last year was that, okay, you have tread damage. It's either shelling, RCF, thermomechanical shelling, whatever the case may be, spalling, or wheel slides. The cracks propagate under rolling and pounding loads. You have this high compressive layer at the surface, which is essentially work hardening. It's generated by rolling and pounding loads, and it has to be balanced by tension deeper. It has to be balanced. So when, I should say, if the cracks propagate into this tension zone, the cracks can rapidly change in service, making VSRs more likely. And Class U wheels, interestingly, seem to have the tension zone deeper. This, and of course, lower loads. When U wheels were out there running around, the wheel loads were a lot less. We're now at 286,000 pound gross rail load, and in those days, a lot of 220,000 pound cars were running around. So certainly there's the effect of wheel load. We don't discount that, but we think that the difference in the softer material pushes that tension deeper. Now, effects of machining. This was interesting. So we said to ourselves, all right, we've got this tread damage. Can we fix this problem? Can we make it go away? And we've looked at a lot of internal things, such as quench time, quench delay, temperature, using finite element, using the U of I model, to see, can we create axial stresses that are really wacky? And at the end of the day, we couldn't create them to such a point that we thought they were dangerous. So we said, we've got to find a way to correct this damage in service and see what that does to axial residual stress. So we get 6 wheel sets with tread damage from one wheel shop, and I note that 2 of these wheels would have been scrapped for thin rim. They were machined as much as they could. The point here is they didn't get a full machining. And the question is, what does truing do to the residual stress distribution? And here we see roll of wheel truing on axial residual stress in used wheels. These were not broken. And we see that the 2 wheels that were not fully cleaned up, that didn't get the full machining because they were too thin, had the deepest compression remaining, and one of those had the highest tension. So just because a wheel is machined doesn't mean you're going to get rid of all of this effect. You may reduce it or eliminate some of it. Interesting to note that the rest of these did seem to flatten out, I'll say, the stress profile without that deep compression and that tension peak. So we've continued on. We got 12 additional machine wheel sets, 6 wheel sets, 12 wheels from CN, and Dennis's group has been very helpful, helping us out with some wheels from Havelock. And we're continuing to test out of round wheels and testing at high and low out of round points around the wheel. Also, we have 4 wheel sets of Class C wheels and 4 wheel sets of U wheels out at the fast train at TTCI to see how quickly the stress pattern develops. And we're going to take those out at various mileage levels and see how does that stress pattern develop in terms of time and intensity over time. Back to the wheel truing issue. At Havelock, we actually recorded the amount of metal removed. For the first 2 tests, we didn't do that. We just grabbed a bunch of wheels to see, does machining reduce it? But for this test, we actually recorded the amount of metal removed by the operator. One was 6/16 and a ½ inch here, 6/16 again, and one was 3/16. This is a very manual operation. The operator dials in a number where he thinks he's going to get rid of the tread damage. And if he sees little rust streaks after the machining is done, he knows he didn't get all the cracks. Then he goes and dials in another amount. So this is a fairly manual operation that must be done by eye. And then we sent these slices out to American Stress in Pittsburgh. Here's some of the tread damage wheels that we later machined. Varying degrees of damage. This was what we labeled number 2. Fairly large chunk coming out of the tread here. Another example, this is wheel number 4. Some quite severe tread damage here.
Do you know how close that tread damage or how deep that was close it is to the tensile stresses?
Didn't measure the depth, but it would have been condemnable. So you're looking at something that's bigger than an inch in diameter with no islands. The AAR manual says you can have an inch, but if it has a little island of good metal within that inch, then it's still okay to return to service. So these were all areas that were bigger than an inch. Depth, I don't know. We didn't measure that.
I don't think there's a criteria for that, it's just
No.
an area.
No, but to our question, we probably should have, now that I think of it, we probably should have measured that. But some of these can get quite bad. Here's one here where you had large numbers of pieces that had come off and many more cracks in the network here. That was number 5, wheel number 5.
So, can I ask you a question?
Yep.
What is the mechanism for this damage?
For,
Why is this thermal cracking, or is this contact oriented?
okay, there's basically 3 types. You have shelling, which is like pure rolling contact fatigue. The second is thermal mechanical shelling, which is when you're drag braking or you have stuck brakes, so your material is getting softer, and therefore fatigue is more likely because it's softer and more fatigue susceptible. The third is wheel slide. We didn't, at this point, etch it with ammonium persulfate to see if it was a slide, because if it is a slide, you're going to see martensite when you etch it with ammonium persulfate.
That's unlikely though, right?
Well, no, it's actually fairly common,
You are-
particularly on a mixed rate car, one where the handbrakes are put on to spot it in a siding at a customer, or if you tie the handbrake on in a yard, if they don't take the handbrake off, which is fairly common, they can slide the wheels. Or in the cases of air brake systems, which can malfunction for service or emergency portions, you can slide the wheels. The AAR Wheel Defect Prevention Consortium inspected several hundred wheel sets, and it was found that coal trains and intermodal trains, the more unit service, are usually thermomechanical shelling, whereas mixed rates like tank cars, covered hoppers, box cars are more susceptible to wheel sliding. So a very large number of cars are affected by wheel sliding because of brake issues.
With all of this shelling, have you looked at the idea of the shelling reducing, you're relieving not a lot of the compressive stress, therefore your balance on your tensile stress should also be affected because you've relieved a lot of that compressive forces that are building up.
As the piece pops out, it changes the stress pattern. Excellent thought. I had not thought of that. Good thought. Yeah, very good thought.
The other thing is you're not getting sufficient wear, or you're not grinding. So you're grinding, some optimum is not being reached,
Exactly.
correct?
Exactly. One of the things we noticed that I didn't put on this VSR puzzle slide was that North America is the only place that I've heard reports of these wheel failures. Australia, BHP and those guys operate very heavy axle loads. They don't have them. South Africa doesn't have them. They don't happen in China. They don't happen in Brazil, which operates very heavy. Europe doesn't see them. So the only commonality that I can think of, and anybody correct me if I'm wrong, is that their tread management is better. In other words, we have these free-running interchange cars that are allowed to get in this condition. For BHP, essentially, it's a conveyor belt from their mine to their port. It's not necessarily a railroad. QCM doesn't see these. Quebec Cartier, I was up there a couple of months ago. Quebec North Shore and Labrador did admit to me that several years ago they saw a couple of these. And I was fascinated by that because it's the only place where, outside of the general North American interchange fleet, where someone had reported these. They said, well, at the time, our tread management wasn't that good. So, this is a lot of anecdotal evidence, he said, she said, but I think the difference is, as you suggest, that we are sub-optimizing our balance between cost of wheel truing and allowing these things to get to the point where they're just ugly.
Same applies to the rail, right, as well.
Absolutely. Nobody ground for years and years and years and years. And people started grinding. A little corrective grinding every now and then may be better than taking a big, so.
Are you in the rail business also?
When I was on the railroad, I dealt with railroad. I don't anymore.
Your company?
No, we are not in the rail business.
You mentioned much earlier in the presentation that you see most of these type of failures in cold weather or wheels that are running in cold weather climates.
VSRs tend to occur more in winter.
Okay.
And CN, in general, has typically had more of these correct me if I'm wrong, Dennis, than I've heard that other people have had.
I think that's true.
And a lot of factors go into this. Wheel impacts are affected by how frozen the subgrade is, by the concrete ties or wood ties. There's a lot of factors that go into that, how much of a wheel impact you're going to be putting into the wheel and the rail. And of course, it's cold in the winter, and then steel is not as forgiving. But again, a 1070 carbon steel is not ductile by anyone's definition.
Do you get a particular type of spalling occurring in winter compared to other times?
Tread damage is much worse in the winter. Yes, it's much worse in the winter. There's been a number of theories on that. First, I've already talked about is brake problems. Air brake systems freeze. Air brakes, the service and emergency portions cause the wheel to slide. Another, there was a theory of hydraulic crack propagation, where you get water inside tread cracks during the winter, and they freeze and opens them up a little, so you get more damage that way. Kind of like potholes in a road. Yep.
We have a question from one of our internet participants about, do you see VSRs in locomotive wheels? And if so, what's the difference between them and freight car wheels?
I know of one. And at the time, it was not my company's wheel, so I don't know much more about it. But I know of only one. They're not common.
Was there any difference between, or do you not know?
I don't know much about it. But the vast majority of these are on freight cars. I've seen one on a locomotive wheel.
Part of the difference might be tread management. It's different between locomotive wheels and freight car wheels.
Well, and the truth of the matter is, if the locomotive engineer is getting a bumpy ride, he's going to tell the shop foreman when he arrives, that thing's bumping, I don't like the bumping. So it'll probably be wheel true. Whereas the coal doesn't really respond if it's bumping, it just goes for the ride, right? So, anyway. There's the truing operation, and again, this is where the AAR 1B profile is being put back onto the wheel tread to kind of restore it. And right in here is where the guy was looking for the little rough streaks. It's amazing, you can see them quite effectively. They pop right out of a shiny surface. Oh, he says there's a crack right there, didn't get it. But where? Because he looks at it, oh yeah, you're right. So obviously you wouldn't want me on the lathe, or you better train me anyway. That's a good point about training. So, these averages, the next graph is going to be the meat and potatoes of this whole thing, okay? The averages for the VSR 1.5, I've got 26 data sets from 21 wheels. For the VSR 3, I've got 19 data sets from 14 wheels. The used Class C is 22 data sets, 13 wheels. We kept retesting some wheels, again, for that circumferential effect, just to see what we were doing, and also across the tread surface. The machined 1.5-inch wheel average is made up of 28 data sets from 28 wheels. Machined 3, 24 data sets, 24 wheels. And there we go. So you see the machined 1.5 is the dark blue, and the machined 3 is the dotted blue. And what we've done essentially is knock the tension peak off and reduce the compression. These are averages. These are averages. I stress that because there's some that are better and some that are worse. But what we've done here is, as opposed to the vertical split rim, 1.5 inch in the front rim face, and vertical split rim 3 inch in the front rim face, and used wheels, we have reduced the tension peak, chopped it off, reduced the tension, and reduced the compression. The next question is, how soon does it come back? And that's what we're going to learn from the TTCI test. How soon does the stress pattern come back in service? If we advocate wheel truing and it's back in 10,000 miles, then we haven't done very much. But we have at least if we wheel true it, we've gotten rid of the cracking and the tread damage, which we believe is sort of the fuse for VSRs. So, some conclusions. Wheel truing not only corrects the tread profile and removes the damage, the divots, the big chunks that come out, and the cracking, it reduces the magnitude of subsurface axial tensile stress, and we believe that's important. For VSR wheels, you basically knock off roughly 8 KSI from VSR to machine wheels, somewhere in that neighborhood, which is not a trivial amount. Wheel truing reduces the chance for a VSR. A VSR needs tread damage, it needs propagating cracks under rolling service and impact loads, and an axial tensile stress of sufficient magnitude below the surface gets those cracks to run, and that's when the wheel is going to break. So it's an A plus B plus C thing. And I think the more wheels we continue to test, the more confidence we're going to have in this model that we've got here. And that's it for any questions. I'm open. Tyler? Yeah, for spalls, the loose car railroading is the most susceptible. I'm not certain if there's any type of wheel that has any type of car that has a more predominant number of VSRs. I'm not sure about that. Definitely for loose car railroading, you get more spalls. For unit trains and intermodal trains, you get more rolling contact fatigue and thermomechanical shelling. VSRs occur on heavier cars, so if it's 263,000 pounds gross rail load or 286 gross rail load, yes, those definitely occur more often than a 33-inch wheel at 220,000. But I can't say absolutely it's one car type or another. Yeah, 15 out of 17 run the BN, so 15 out of 68. So 68 wheels that they looked at, 15 of those were on covered hoppers. I'd have to go back and look at that presentation. It was in one of the BNSF meetings. I think it was 07, 08, or 09. But that would have the breakdown of car types in there. Yeah.
When you get these failed wheels, you get them as isolated wheels, right? Not wheel sets?
Well, the railroad gets them as sets. And Dennis, how do you guys get them? Do you get them as sets at the lab?
Yeah, close to the back.
Okay, so then they'll be shipped to a point on the railroad that we'll look at them. And then when we're brought in, we want to look at them knocked off the axle because it's just too difficult for us to cut them.
Because, well, I guess what I'm getting at is if we know anything about the opposite wheel on the wheel sets and subject to defects. Kim Bowley from CSX presented here a couple of years ago on geometry defects and had a theory that a substantial number of geometry defects, rolling geometry defects, were a result of certain threshold difference in the wheels, so different radii, two different circumferences of the two wheels in the wheel set. And it makes me wonder, and the effect that she was looking at was, the result of that was that you have an axle that's essentially one of the two wheel flanges essentially riding against the edge.
The shift or the parallelogramming. Yeah.
So what makes me wonder about this is whether you could ascertain whether the wheels that are suffering VSR are coming from such a wheel set where they are essentially riding laterally out of place on the rail, so you're putting more stress on the weakest part of the tread.
That's a really good thought, and you know, I'll take that back to our railroad partners, and you know, maybe they could just note that. You know, is the opposite flange worn, or is there anything unusual about the wear on the wheel? Because historically, when we've gotten them, they've been demounted and loose.
Because even tape size, even throwing the
You're right.
tape size might be interesting.
You're right. That's a good point. That is.
Scott Cummings has a question.
Okay. Hey, Scott.
Has Griffin tested axial residual stresses on their worn freight wheels that have been used on other continents?
No, not yet. And the reason we haven't is because there's no failure problem there. But that's a good point, Scott. Yeah, that is. Yeah. See if there's anything different going on.
You said VSR always starts with tread damage, and the drop hammer test to reduce didn't make any VSR actually. And can it be indicated that because the drop hammer test did not make VSR is because the drop hammer test did not result in a shelling or powder?
We did have shelling on that. I've got to find that slide. Well, I'll show it to you afterward. But the wheels that we selected for the drop hammer were pretty bad. We had found those wheels at a wheel shop, and they had large areas of tread damage. So we picked one with tread damage with the assumption that if we hit it hard enough, it would break off.
So there must be something left to make a crack on the tread surface.
Yes. Rolling contact fatigue, rolling contact fatigue with heat, which we call thermomechanical shelling, which is you're going down grade with heavy braking for a long period of time, or your brakes are stuck, or wheel spalling, where you slide the wheel, you transform to martensite. I didn't put that stuff in here. That's sort of another presentation, but I've certainly got a lot of stuff on what causes spalling, what causes RCF, and that sort of stuff. But if you slide the wheel, you transform it to martensite, and very hard, very brittle, slightly larger in volume, and that piece will pop out too.
Probably didn't mention this in the presentation, but in the paper you argue that possibility of wayside detection, detecting GSRs.
Yeah, this is sort of out there. This is going to be hard to do because if you've got 300 of these a year that fail, and thousands of wheels are removed for high impact loads, what I think we need to do is work towards some kind of a rules engine that says, okay, if a wheel has been impacting at higher than a nominal load for some period of time, then maybe we look at that one. I think it's going to require something like KIP miles, in other words, impact miles, impact days, combined with something I call the ugliness index, the tread damage. If you have a wheel that's been impacted for a long time but doesn't have any tread damage, if it's healed, the tread damage, and it's sort of just kind of an egg shape, that probably is not a good candidate for a VSR because there's no fuse, there's no crack. So you have to have some way to judge the amount of tread damage. And if you judge the visual appearance of it, you're sort of extrapolating depth, which isn't always right either. Because again, it's the depth of that crack. The longer it stays out, the worse it's going to get. So some kind of a rules engine of KIP miles, KIP days, plus tread damage may be able to be predictive, but it's going to be hard. The other thing we have is the ionics division of our company that has onboard monitoring. And maybe onboard monitoring could tell you, okay, position L1 on the car is really impacting hard, has been for a long time. That might be another way to do it. But this is, I tell people if we had 10,000 of these out here in the parking lot, it would be an easy problem to solve because it would jump out at you. But with 300 out of a freight car fleet of 1.5 million, it's difficult. But we got to fix it because, nobody wants wheels to break. He doesn't, I don't, nobody does. Yep.
You showed a picture of a VSR within a VSR,
Mm-hmm.
but it wasn't clear from the picture what crack
Okay.
was propagating from one.
Okay, let me go back to that. There we go.
Yeah, so where is,
Okay, we're at the slide that says two adjacent VSRs, axial residual stress measurement pattern. This piece broke off here. This used to look like this.
right,
That piece broke off. This is in here cracked. So what's happening is that this crack, which goes into the page and out of the page and broke off, this crack is also doing the same thing.
but what propagated that inside crack? It doesn't look like.
Well, you may be looking at the tail of it. See, as you go around circumferentially, it'll reach the surface. So there, at some point, and I don't know where back here on the circumference of the wheel, but that intersects the surface, and I guarantee you'll find a big blob of tread damage there. So what we're seeing is the tail of this crack as it propagates out of the page. And we thought, well, what we're doing here is we thought we were, reaching a point here where we could just cut a slice, and we found another one inside. It was serendipity. It was kind of interesting.
But normally, your VSR observations are that the wheel gets, broken up, the part broken up, not as much to the edge like that, because that's not where your thermal cracking is trying to occur as much as further to the left, right?
Yeah, so basically this piece here is missing.
Yeah, but normally, do you get that piece missing, that far to the right, or does it happen more toward the middle?
The observations by Matt Dick and those guys was it was roughly an inch to 3. So you can get it an inch, 2 or 3 inches, depending. Obviously, if you're out here on this cantilever beam, you tend to have more of them kind of outward from the tape line, as opposed to this big thick section. But they have happened in here occasionally.
Does the tread damage change the magnitude or the direction of the stresses in a more critical way?
I think what's happening is you have the tread damage, which is essentially a hole that every time the wheel comes around, bam, it hits. So that impact is cold working. You're cold working the material at the surface. You're just pounding it. You get more compression at the surface from that impacting. It's like you're banging on something with a hammer. And then below the surface, since you plastically deformed it, since you have permanent deformation, below the surface you have to have balancing tension. So you're really getting an increase in magnitude, and it probably affects the hoop stress too, but there's no real easy way to measure that.
But does that show up on a live detector the same as the out of ground wheel?
Okay.
Is the thump the
Yes,
same?
well, a thump is going to be a thump, be it from a hole in the wheel, where you're just coming around and impacting, or a wheel that is slightly out of round for whatever reason. Sometimes the tread damage will heal itself, sort of, it'll kind of wear itself into an oblong shape, so you don't always see the damages clearly. But if you do a TIR on it, the NSF has a nice little system with a laptop where you can, look at your maximum point of out of round. Sometimes it'll be an area that doesn't have a lot of tread damage. But, for that wayside impact detector, a bang is a bang.
But if we improve the detection system such that we can differentiate between the out of round thumb and the tread damage thumb, then we'd be able to flag the tread damage thumb.
It's a good point. If you can combine it with a picture, yeah, good point. Yeah.
Can you contour the wheel a little differently so that your contact moves closer to the flange as well as your brake shoe moves closer to the flange? Then you wouldn't be getting this wheel, right?
It's a fair point. And also gauge plays an important role, because if your track gauge is wide and you're running out here all the time, that thing's just wanting to break open. So the gauge is important.
The point was asked about the locomotive wheel. I mean, the locomotive wheel is 44-inch diameter wheel, right?
40 or 42. There are some 44s on the,
Okay.
yeah,
And what is the diameter of this wheel?
36.
Okay, so there's
36.
a difference in the gauge. That's what you mean.
Well, no,
What do you mean by, I mean, I'm talking about,
well, track gauge.
Track
If your rails are a bit wide and you're riding out here all the time, that'll lead to more bending.
but if you change the diameter of the wheel,
Mhm.
this cross-section changes as well, correct?
That's correct.
Okay, but also the contouring is the same? That's the AAR?
AR1B.
We have another question from our callers. Phil Dahm of VSI. Have you etched the sawed surface to study the deformation of grains in the area of the cracks?
Phil, over the years, we've looked at a lot of macro etches and a lot of micros. On these particular slices, we've not done that. But yeah, you can see cold work layer, and that's why you got compression.
So if we only experience 300 or so VSRs, do you think it's more cost effective to have better tread management, or with new research to have a stronger wheel?
Well, short answer to your question, I think better tread management is probably in order. The question is, how expensive does that become? And this is why we want to do this test at TTCI, where we see how fast, how quickly the pattern redevelops, and then does it increase in intensity over time, or what happens to it. Again, if I tell you, oh yeah, you got to wheel through it every 100,000 miles, but the profile and the pattern comes back at 20,000, you've accomplished two things. You got rid of the tread damage, you got rid of the cracks. Those two are good things. But your stress pattern, if it comes back, that part of the equation is over. But I think if you don't have the fuse, you're not going to get the VSR. And that's what we've seen, again, with Europe and with Australia and Brazil and China, is they don't have these failures, and they tend to look at their treads a little better. We watched the Quebec Cartier mining train go out of the yard, and it was the quietest train I ever heard. An iron ore train. It's the quiet. And their impact detectors are two men, one standing on each side of the train. And if there's anything that bangs,